In this video, we're going to look at solving logarithmic equations using the definition of logarithms. In particular, we're going to solve logarithmic equations using the definition of a logarithm along with the use of the product, quotient, and power rules for logarithms. Let's begin the discussion of logarithmic equations by recalling the definition of a logarithm. The logarithm base b of x is equal to y if and only if b, the base of the logarithm, raised to the y power is equal to x. If we have an equation where there is a single log on one side of the equation and it's equal to a constant, we can simply use this definition to convert our logarithmic equation to one in exponential form and then solve the corresponding exponential equation. For example, let's solve the equation log base 2 of 5x plus 2 equals 4. This is an equation that is in logarithmic form. We have a logarithm on the left side and we have a number on the right side. If we go to convert this to our exponential form, we're going to start with our base 2, raise it to the value of our logarithm, which would be 4, so 2 to the 4th power, and that's going to equal the expression inside the log, which is 5x plus 2. So we have the equation 2 to the 4th equals 5x plus 2. And we can easily solve this. This is just a linear equation. 2 to the 4th, of course, is 16. And so to find x, we can simply subtract 2 to get 14 equals 5x, and then divide by 5. And we see that x is 14/5. Now, it's important with log equations that we always check to make sure that our solution is defined in the original equation. If we take this solution 14/5 and substitute it in to 5x plus 2, what we get is a log of the number 5 times 14/5 plus 2, and this is going to be the log base 2. When the 5's cancel, we have 14 plus 2 of 16. Which of course is equal to 4. But in this case, what's really important is that this number inside the 16 is a positive number. And since it's positive, this logarithm is defined, and 14/5 is in fact a solution to this equation. If we had substituted our value in and we had gotten the log of a negative number, then we would have to discard that solution since any logarithm is only defined for positive values. For a slightly more complicated example, let's look at the equation log base 2 of 2 plus log base 2 of 3x minus 5 equals 3. In this case, we don't quite have a single log on one side. We have the sum of two logs. But both logs are base 2. And if we have the sum of two logs with the same base, we can apply the product rule for logarithms in order to condense that into a single log. And so on the left side, we're going to do that. We're going to rewrite that using the product rule as the log base 2 of 2 times 3x minus 5. And that, of course, will still stay equal to 3. So what we have here is the log base 2 of 6x minus 10. That will equal 3. And we can apply the definition of logarithm to this new equation. And so we have 2 to the 3rd power, which of course will be 8, and that will equal 6x minus 10. We'll solve for x by adding 10 to both sides, so we'll get 18 equals 6x, and dividing by 6, we get an x value equal to 3. Again, we do need to check that this number works in our original equation. The only log term here with an x is the second one, log base 2 of 3x minus 2. And here, when we substitute that in, we see that we're going to get 3 times 3 minus 5. So this will be the log base 2 of 9 minus 5, which is 4. And that is a positive number. So this solution checks out. And x equals 3 is our solution. For another example, let's solve log base 6 of x minus 9 plus log base 6 of x minus 4 equal to 2. We're going to approach this one much like the last example. at least to get started. On the left side, we have the sum of two logs with the same base 6, and so we're going to apply the product rule to condense that into a single log. So here we're going to have the log base 6 of x minus 9 times x minus 4, and that's going to equal 2. We're now going to work out the product inside the logarithm here, and x minus 9 times x minus 4 will be x squared minus 4x minus 9x is minus 13x plus 36, 9 times 4. That, of course, will equal 2. At this point, we have a log equaling a number, and so we can convert this to exponential form. We're going to have 6 squared equals x squared minus 13x plus 36. And of course, we have a 36 on both sides. This is, of course, equal to 36. So we could subtract 36 from both sides, and we'll obtain 0 equals x squared minus 13x. This can factor by factoring out an x as a common factor, and we're left with x minus 13. And so we get two solutions here. We get an x equal to 0, and we get x minus 13 equal to 0, which gives us x equals 13. These are our two potential solutions for this equation, but we always have to check with logarithmic equations. With x equals 13, notice that if I substitute it into the second log, I get 13 minus 4, which is 9. That's okay. It's a positive number. And if I substitute it into the first, I get the log of 13 minus 9, which is the log base 6 of 4. Again, that is perfectly fine. And so x equals 13 checks out as a solution. However, if we try x equals 0, and we try it in either of these two expressions, for example, log base 6 of x minus 9, we're going to get log of 6 of negative 9. And this is undefined. And so this is a warning. Once we see this, we know that 0 is an extraneous solution. It was one that was added by converting to exponential form and using the quadratic function, or the quadratic expression inside the logarithm. And so 0 is not, in fact, a solution to this equation. In fact, the left side of the equation is not even defined when x is 0. So x equals 13 is our only solution. If you'd like to try a similar example, try to solve the log base 2 of x plus 2 plus the log base 2 of x minus 1 equaling 2. It turns out that there are two potential solutions, just like in the previous example, and one of them will work and one of them will not. In just a few seconds, the answer, including both potential solutions with the proper one indicated, will appear. For one last example, where the answer might involve the number e, let's consider the equation 2 natural log x plus 3 equaling 7. Our goal should still be to get the logarithm isolated on one side and a constant on the other, but in order to do this, we need to do a little bit of algebra. We need to subtract 3 from both sides, which will yield 2 natural log x equals 4. And then we do need to divide both sides by 2. And we're left with natural log of x equals 4 divided by 2, or 2. At this point, we want to solve for x by converting to exponential form. We need to remember that natural log is the logarithm base e, and so natural log of x equals 2 is the same as the base e raised to the second power equaling x. And so here we get a solution of the number e squared. This number will work when we substitute it into the natural log in our equation. We do get a positive number. In fact, we get 2. So we even know how to evaluate that, unlike a lot of cases. But in this case, this is our own solution, or our only solution. So whenever we have an equation that just simply involves a single natural log x like this one, you should probably expect your answer to involve some power of e. If you'd like to practice with a similar problem, try to solve the equation 2 times the natural log of x plus 1 equals 10. The solution will appear in a few seconds.